So I wanted to introduce the idea of Newton's laws because in chapter 5 we learn about Newton's laws, and then in chapter 6 we learn how to apply them. And so this is different from what we did before when we studied motion in chapters 3 and 4. But while we did make reference to gravity in some cases, we never really discussed in depth the forces that cause the motion. And so this is where we make that transition. In chapters 5 and 6, we're really concentrating on the idea of how do the objects move the way they do? What are the forces responsible? And Newton came up with his 3 laws of motion that help us to explain that. So the first thing we have to do is we have to understand what are some certain types of forces and what do we mean by that? So there's a couple different ways that forces can occur. One, a force can be just caused by something pushing or pulling on an object. It can also be due to the interaction of 2 objects. One example of that is gravity is actually due to the interaction of 2 masses with each other. It can also be due to the interaction of the objects with their environment. Friction would be a good example of this because when we learn about friction, we'll learn how it's the interaction of the 2 surfaces that causes that. So that's another one that falls into that category. What we do have to remember, and this is why we learned about vectors, is that force is a vector. And so when we're working with forces, we have to worry about their vector nature, which means sometimes we're going to break them into components, and we absolutely always have to worry about their direction. So what are some different types of forces? So we're going to look at 4 really common types of forces. The first one is the normal force. So a normal force is called normal simply because it's always perpendicular to the surface. So it doesn't mean that it's regular. It's normal because it's a math definition. It's normal to the surface. The normal force is the force that an object feels when it's resting on another surface. So a book sitting on a table, a box sitting on a floor, a box on an inclined plane, all of these will feel a normal force, which is due to the surface they're sitting on that pushes up on the object itself. The direction of that force, if you didn't guess, is perpendicular to the surface itself, which is why we call it normal. It's also known as what we would call a contact force, because if our box was hanging in the air, it wouldn't feel a normal force because it wouldn't be sitting on a surface. Friction is another force that we're going to learn about. Again, a contact force because it's due to the interaction between the object and the surface that it's sitting on. We're also going to learn that friction is always going to be directed in a direction that opposes the motion. If the thing is moving to the right, friction's going to act to the left. Tension is another force that we deal with, and tension is always going to be due when you have a chain or a rope or something that is attached to the object, and we can exert a force on it. We say that the force then is due to the tension in the rope, for example. The interesting thing about tension is always going to pull on the object. And I think if you think about the nature of a rope, this makes sense. You can't push on a rope and get it to exert a force. It always has to be pulling away from the object. Tension is also going to be considered a contact force because it's due to its direct contact with the object. And again, it can only pull, it can't push. Weight. Things weigh something. The weight is due to the force that an object feels due to gravity. Now, for instance, we might not have thought about it too much, but the reason that you have weight is because the earth is pulling down on you with the force of gravity. And so that's what causes your weight. Now, gravity, we'll learn about gravity in more detail in a later chapter, but gravity is a force that exists between 2 objects, but the objects don't have to touch. When we think about us standing on the ground, we might think, oh yeah, but we're touching the earth. So it's not a great example, but if you want to think about, say, the sun and the moon or the sun and the earth, they're not touching each other, but they are exerting the force of gravity on each other, even though they don't touch. And so we classify weight as a long-range force because it's due to gravity, which is a long-range force as well. Forces are vectors, like I said before. When we want to use the units that we measure force in, it's going to be newtons. And so we use a capital N as an abbreviation. That's in the MKS system of units. If you haven't caught on to that yet, we tend to use units that are based on meters being used to measure length, kilograms being used to measure mass, and seconds being used to measure time. And that's where MKS stands for. That's the units system that we're almost always going to use. If you want to say, well, hey, I never heard of something being measured in terms of a newton, you're right. We use the imperial system, and so we're using pounds as our unit of force. Got to be different. So what is Newton's first law of motion? Newton's first law of motion answers the question, if there is not a net force acting on an object, how will it move? And so Galileo actually sort of thought through this and came up, or like sort of got towards the point where Newton could come up with the answer to this. And that is that, think about a slippery surface, or if you push a book against a table, it'll move for a while and then it comes to a stop. And you know that that's because of friction. If you took that box and that book and you moved it to the ice rink and pushed it with the same force, it would actually move for a lot longer because the ice is a lot slipperier. And if we sort of keep thinking about going towards a surface that offers less and less resistance until it offers no resistance, we would realize that once that book started moving, it would never stop because there would be no force bringing it to a stop. That's what Newton's first law says, is if the total force acting on an object is zero, how will an object move? And right here it is. It says, an object in motion will continue in straight line motion, that's important, and an object at rest will stay at rest in the absence of a net force. So basically, it's going to want to keep moving if it's already moving. And if it's sitting still, we never expect it to start moving without being acted on by some sort of force. Newton's first law is usually referred to as the law of inertia. And because the reason for that is, as I said, it describes how an object moves as there's no net force acting on it. Inertia actually refers to the resistance of an object to a change in its motion. We use inertia in everyday language where we talk about people not wanting to change and there's a lot of inertia. In a way, it kind of is defined in physics in the same way, but a little bit more specific. The inertia of an object basically sort of quantifies how much it doesn't want to change its motion. And then if you think about, well, how would be the best way to quantify that? The answer would be its mass. So for instance, if you have a ball coming at you as you're playing baseball, the ball's coming at you 80 miles an hour, the baseball player can change its motion with the hit of the bat relatively easily. So while the ball is moving really fast, its inertia is really quantified by how massive it is, which is not really very massive. However, if a car came at that batter at 80 miles an hour, he would not try to hit it with his bat. He would leave. He would run away because he knows that that car has much more inertia than the ball did, and there's no way that he's going to be able to change its motion. So, just to recap, Newton's first law is known as the law of inertia because it talks about the fact that objects want to keep doing what they're doing. They want to keep the motion that they have. So that's why we say objects in motion want to stay in motion, and objects at rest want to stay at rest. So Newton's second law then answers the question, well, what if there is a net force? And so we say that the net force, and that's what the sigma is standing for. I didn't mention it earlier. That giant sigma means the sum of, like if I added up all the forces, and that's equal to the mass times the acceleration. And so basically Newton's second law says if there is a net force, because remember, the first law talked about when the net force was 0. Second law says, okay, what if there is a net force? And it basically says that the object will experience an acceleration. Furthermore, if you rearrange that expression, you would see that the acceleration would be proportional to the net force and inversely proportional to the mass. So for a given force, larger masses have smaller accelerations, and if you have a larger force for a given mass, you're going to get a bigger acceleration. I think we already said that the unit of force is a Newton, but here you can see how it comes together using ma is equal to force, the mass is in kilograms, the acceleration is in meters per second squared. Now that we see that, we can do a little bit more and talk a little bit more about weight. So the weight of an object is equal to the force that the object is experiencing due to gravity, which means that its acceleration, if it's not sitting on a table, but if it's in the air, would be the acceleration of gravity. And so the weight that an object has is simply equal to mass times gravity. And so we're going to be using that expression a lot when we talk about the force that an object is experiencing due to its weight. We'll always label it. We'll say, okay, here is the box. The box has the force due to gravity acting on it, and we'll just call that mg, because that will indicate what its weight is. Now, something that we're going to encounter when we study gravity in more detail is the value of gravity does depend on the altitude. Like that means like how high you are above the surface of the earth. It actually gets smaller. Not that quick though. People think it gets low really quick, and it's not true. But it does depend on altitude or how far you are away from the center of the earth. And the other thing that we have to think about is that on other planets, the force of gravity will have a different value. Well, that's it for introducing Newton's first and second law. Hope you enjoyed it.